So at this point, all of you know as much about the price of anarchy with simultaneous second price auctions as anyone in the world. I'm not kidding. So, so not much more to say about that. But I do want to show you that there are some other auction formats. And for this lecture, I actually just want to focus totally on first price auctions. Even for single item auctions, it's sort of interesting to talk about first price auctions, which we haven't done yet. But then we'll also be able to extend those results to simultaneous first price auctions. By which, of course, I just mean you actually pay your bid. You don't pay the second highest bid. If you win, you really pay what you said you'd pay. And both this quarter and last quarter, we have talked, we've talked very little about first price auctions, at least in comparison to second price auctions. And the main reason that that's been true is because of our focus on these strong incentive compatibility guarantees, these DSIC guarantees, which of course the Vickery auction has and the first price auction hasn't. So the first price auction just hasn't come up very much. But actually, now that we're talking about these simultaneous auctions, right? I mean, it's not like using the second price rule, right? You certainly don't have a dominant strategy in these simultaneous second price auctions. We know that. In fact, if you just think intuitively, this is not a rigorous statement, but it's not even clear it helps it being easier to play at all, right? In a single item auction, it's great. You don't reason about the rest of the world at all. You just bid your valuation. It's guaranteed to be good. If it's the simultaneous thing, if I asked you, which would you prefer? Would it be easier for you if I used a second price rule or a first price rule? Probably a lot of people would say a first price rule, frankly. Like it might actually be easier to reason about how to bid in one of these with a first price rule. Certainly though, at least, first price rule would be at least as well motivated, if not more so than the second price rule, once we pass to these sort of, simple mechanisms for complex settings, okay? So, and actually, as we'll see, we'll be able to get better bounds for first price rules. So we'll do even better than we did in the second price case, which is pretty cool. All right, so let me just sort of remind you of the very, very basics. So I'm going to talk for the beginning part of the lecture, even just about a single item, okay, which we have talked about some now and again. But so just to remind you, suppose there's just one item. And sort of the canonical example would be you have n bidders, IID, let's say uniform distribution. Between 0 and 1. Okay? Certainly there's no dominant strategy. You want to shade your bid. The amount by which you want to shade your bid sort of depends on what other people are doing. And, but in this case, there's a unique Bayes-Nash equilibrium. And so given that your value is VI, you want to shade it, and if everybody's uniform 0, 1, the amount you want to shade it by is exactly an n-1 over n factor. So we certainly talked about this when n equals 2, and we did a derivation on the board showing that bidding half your value is optimal, assuming the other player is also bidding half their value. Same calculation shows this. In fact, more generally, if all bidders are IID in a first price auction, there's a very nice explanation of what you should do at the Bayes-Nash equilibrium. You should say, well, suppose I actually am going to win. Suppose I actually am the highest bidder. Then let me condition on that fact, right? That's sort of the only relevant case for me is when I am the highest. And then conditional on the event that I have the highest valuation, what is the expected value of the second highest valuation? Okay? So like think if there's just two bidders and we're both uniform 0, 1. Okay? I have some valuation, 0.6 or whatever. Condition on me being the highest. Okay, well now conditional on that, the other person's uniform between 0 and 0.6. And the expected value of the other person is 0.3. Okay, and so in that case I bid exactly, so this bidding half your value is exactly bidding your expected value, the expected other person's value given that you're the higher one. Same thing here, this is the expected second highest given that you're the highest and everybody's uniform. And actually that exact same formula gives you the unique Bayes-Nash equilibrium for any IID setting. It's not that easy to prove uniqueness, but it can be proved, okay? Right, and so this is also sort of intuitive, I think. So basically this says as the competition increases, you can get away with shading less and less and less, okay? Yeah?
Wait, when you say unique, you mean there's no other equilibria?
There's no other Bayes-Nash equilibria in the IID setting, okay. Exactly. But that's not very easy to prove. That takes some work, okay? What's not too hard to prove is that there's no other symmetric equilibria where everybody uses exactly the same bidding function. So notice here it's symmetric, right? So this formula does not depend on I. What's sort of a pain to rule out is asymmetric Bayes-Nash equilibria, where different people use different bidding strategies, but it can be done. Okay, good. Right, so as the competition increases, you can get away with shading less and less, okay, which sort of makes some sense. Okay. All right, so as a consequence of what I just said, in IID settings, it's not very interesting to talk about the price of anarchy. Okay, but the news is good. Price of anarchy is simply equal to 1 in IID settings. Okay, so in the unique Bayes-Nash equilibrium, everybody follows exactly the same bidding strategy, and the amount that you bid is strictly increasing in your value. So if everybody uses the same bidding strategy that's strictly increasing, it means the highest bidder is always going to be the person with the highest value. And that means you have full efficiency with probability 1. Okay, so that's great. So IID case, single item auction, first price, no problem. Okay. Okay, now let's just even, stick with the m equals 1 case for now, but relax the IID assumption. Okay, so we'll stick with it being independent, right? The results last lecture, we needed a product distribution, but we certainly never used identical distributions last lecture. That never came up at all. So let's think about distinct independent distributions. And now, this is no longer true, okay? So if we're running a second price auction, wouldn't matter, right? You don't need a prior at all for the second price auction. As long as players play dominant strategies, you have full welfare. First price auction, if you pass to priors that are not ID, you lose the full welfare property, okay? So I'll leave this as an optional exercise. That the Bayes-Nash price of anarchy can be strictly less than 1. Even if, say, the first bidder is uniform 0, 1, and the second bidder is uniform 0, 2. Okay. So what does it mean that the price of anarchy is strictly less than 1? It means that, with positive probability, the person with the smaller value wins, i.e. winds up with the higher bid. Now, sort of some very hand-wavy intuition about why this happens. So remember, in the IID setting, the calculation is such that the more competition there is, the less that you shade. Okay. So if these two people, there's two bidders here. So if they're exactly the same, then the equilibrium would be bid half your value. Okay. Now, as I make them different, if from this guy's perspective, if this guy actually has double the valuation as before, then intuitively the competition is stiffer, okay? So if this guy was uniform 0, 1, this guy would want to bid half his value. I make this uniform 0, 2, so I make these larger valuations. That's like a more competitive environment from this guy's perspective. So it's going to bid more aggressively. It's going to bid more than b over 2 at an equilibrium. Similarly, this guy, because the competition is so weak, this guy might want to bid less than its value over 2, okay? So with this guy bidding more than its value over 2, this guy bidding less than its value over 2, there's an opportunity for an inversion. It's not likely, but there's positive probability that in fact the first bidder will win with a higher bid despite the fact that its value is actually lower than that of bidder 2. Okay? So that's what happens. And again, on an optional exercise set that I'll post at some point, I'll sort of tell you the formula for the bidding function, then it's easy to verify, okay, if you're interested. All right? So that's what can happen. All right, so there's already non-trivial welfare loss, even one item, even just different uniform distributions. Okay? Another thing I want to mention, which is well known, is that it's hard to solve for Bayes-Nash equilibria. Okay, so even here, it's known, so this is a solved case, but the functional forms are not especially simple. They're not simple linear functions or anything like that. Going even much beyond this is quite difficult. So let me give you an example. So Vickrey, of the Vickrey auction, in his paper, which introduced the Vickrey auction, so this is 1961, he derived this formula. So we keep talking about his DSIC auction, but he talked about Bayes-Nash equilibria in auctions too, and he derived this formula. And he offered as an open question, well, I wonder what the Bayes-Nash equilibria are when they're not IID. Actually, I even wonder what it is when there's two bidders that have different uniform distributions. So just uniform distributions with different supports. So he posed that question in 1961. And he guesses when that problem was solved. Two bidders, uniform distributions, different supports. 2 years ago. Okay, so it was 50 years before someone did the 30 pages of computation necessary to figure out what the Bayes-Nash equilibrium is when you have two bidders with uniform supports that are different, okay? So, if you can get your hands on what equilibria look like, that's great, because then you can reason about all sorts of things about them, but you're just not gonna get very far, okay? Even just first price auctions, two bidders, different distributions. Now, fortunately for us, if all we wanna do is bound welfare loss, talk about the price of anarchy, we don't need to know what the equilibria look like, right? At no point have we ever had actually a very solid understanding of what equilibria look like in routing games, in facility location games, or last lecture, okay? We just we use the equilibrium conditions to derive lower bounds on equilibrium utility, and from that we deduce sort of macro properties, global properties about the welfare. Okay, so for first price auctions, I would argue the price of anarchy sort of approach is particularly well motivated because it's not clear how else you would ever get a grip on the welfare of equilibria beyond the most trivial or beyond symmetric environments. Okay. All right. So, first price auctions. So I'm happy to report we'll be able to use the same general analysis paradigm that we used last lecture for simultaneous second price auctions. And the paradigm we used last lecture was to, really the last two lectures, was to figure out some inequality of this form and then to use this doppelganger trick to extend it to Bayes-Nash equilibria. All right, and again, if at all possible, we want to avoid having to manipulate prior distributions in our analysis. So if we can get the extension theorem idea to work, we want to use it, okay? And so that's what we're going to do. So what I want to do next is I want to just prove an analogous inequality to this for the first price auction case. And I'm going to show you actually yet another trick, another tool for your toolbox, which is I'm going to show you how we prove an inequality like this just for a single item. And that's going to be good enough to extend it to an analogous inequality when you have multiple items, okay? So we're first just going to prove a smoothness-like inequality for a one-item first price auction. We're going to do what's then called simultaneous composition to prove smoothness results. Again, it's still going to be in sort of the full information case roughly, but we'll move from one item to many items using simultaneous composition, and then we'll use the doppelganger trick to go out to Bayes-Nash equilibria for simultaneous first price auctions. Okay. And this is sort of the state of the art. I mean, this is really the cutting edge toolbox for how we can prove welfare bounds for simple auction formats, what I'm showing you right now. Okay. Okay. And again, right. And so let me just remind you. So the B stars, function of V bar, but not B. So we definitely still want that property as well. Okay, so warm up. M equals 1. So what does this look like when there's only one item? Yeah. So there's going to be some tweaks. So there will be a couple small changes as we pass from second price to first price, but we'll see those as they come out. So we need some, at least analog, something that looks basically like this. So we need, okay, so there's only one item. We're just coming up with these, deviation bids, so just single numbers. So we need B star 1 up to B star n. And again, function of V bar, but not B, such that the usual thing on the left-hand side. I'm just going to write this part out. But now these simplify if it's just a single item case. Right, so if it's single item, you just give it to the highest valuation. Right, so this is just V max, right? What about this? So if we're in this situation, we have a single item first price pricing rule. What does this boil down to? Actually, it doesn't even matter if it's first price. So remember what this is. This says basically you had some bid profile B. These are the items. Yes, this is in the more general context. This is the items that I wins with the bid vectors B. Right, so everybody wins nothing except for one person who wins the item, and that's the person with the highest bid, right? Yeah. So this just becomes minus B max. Okay? So again, all I've done is I've taken what was sort of evidently the workhorse of everything we did for second price auctions, and I instantiated it for the single item case, and this is what we got, okay? So this is the kind of thing we're looking for, all right? The question then is, can we do this? And what does do this mean? It means construct B star 1 through B star n, construct the hypothetical deviations given the valuation profile of V. Now, we could just try to, use the exact, we already solved this problem for second price auctions. We figured out how to choose these B star i's. So in the second price case, we said basically, look at the items you win in the optimal solution for the valuation profile and go all in. So this is a single item auction. So everybody but one person loses in the optimal allocation, so they'll bid 0. The person who wins in the optimal allocation goes all in. That means they bid their value. Okay, so it means the bidder with the highest valuation just bids it in its hypothetical deviation B star I. Everybody else bids 0. So is that going to work? So what I'm asking you is, suppose we set the B stars exactly as in the second price case. Is that going to prove an inequality of this form? So let's look at these terms, okay? So remember, we're looking at the utility of a bidder. Everyone else keeps doing what they're doing in the bid vector B. This one person switches to B star I. Okay, so there's all the people who lose in the optimal solution, right? So they bid 0, that summand is just 0. So no, that's not interesting. So the only interesting bidder is the one who wins in the optimal solution with the highest valuation, V max. And in its B star, it bids V max. So what is its utility when it bids V max? 0, right? This was like lecture 1 last quarter, right? First price auction, you never bid your value. You're guaranteed 0 utility. It's never a good idea, basically. Okay, so that for the first time is showing, so now for the first time we see why we need to do something different, at least a little bit different, for first price auctions versus second price auctions. We can't use literally the same hypothetical deviations B star, okay? So observe, and needless to say, this, we have no control over the right-hand side. The right-hand side might be, a super positive number, right? Because B is basically arbitrary. So the B's could be small, the highest value could be big. So 0 is, is not going to cut it on the left-hand side. So observe, all of B star i's don't work. Okay? But what's cool is there's a super simple tweak which works. Okay, so here's what we do. Solution, we're just going to choose B star I to be half the value. Okay? So the full value. Right, so you just hedge. Okay? Now, based on what I just told you, the obvious definition of B star would be if you lose in the optimal allocation, you bid 0. If you win in the optimal allocation, you bid half your value. I'm going to do something a little different for a reason that will become clear in a second. So I'm just going to go ahead and also let people who don't have the highest value go ahead and use half their value instead of 0. Okay? We could have done that in the second price case too. It would have been fine, actually. It doesn't matter. Okay? So that's the difference. Half your value. And so now going all in a first price auction to hedge, you only bid half your value. So how does this work? So we get a version of this. We don't get exactly this. So the claim is that sum over I equal 1 to n, ui B star I B minus I is at least half V max minus B max. Okay? And this is for all V for all B. Okay? So it's a version of this, and it'll be good. So the proof is easy. So first of all, because people bid at most their value, their utility is going to be at non-negative, right? Either you lose or you win at some price below your value. So the left-hand side is definitely non-negative. So if the right-hand side is non-positive, we're done. Okay? Not interesting. So there's only something to prove if half Vmax is strictly bigger than Bmax. But in that case, on the left-hand side, when we actually get to the bidder, when we consider the bidder I with the highest valuation, in its B star I, it's bidding Vmax, half Vmax, excuse me. It's bidding half its value, okay? And so if half Vmax is bigger than Bmax, then that bidder I is actually going to win when it deviates. Okay? One thing to keep in mind, I mean, just to be clear, so we're proving this for every possible bid vector arbitrarily crazy. And actually, one thing that's cool in the first price world is we don't even need to worry about overbidding. Overbidding just takes care of itself. So one case here is that all the B's are like a trillion. Okay? But that's not our problem, because then the right-hand side is going to be negative. No big deal. All right? So we don't know. So even when the highest bidder deviates to bid half its value, we're not sure it's going to win on the left-hand side. Always. But if it's the case that, else bidder, so in the interesting case it does win. Else bidder with highest val wins. So bidder I in BI star B minus I. So UI BI star B minus I is at least its actual value for the good minus what it has to pay for it. It's a first price auction, so it has to pay its bid. Its bid is 1/2 Vmax, also known as 1/2 Vmax, which of course is at least the right-hand side. Okay? That's the proof. It's just kind of a trivial proof. It should feel a little loose, actually, and it is. And I'll talk about optimizing it later, okay? But proving this factor 2 is just very easy, right? So, any questions about that? So we took the inequality that we knew was super important, we specialized it to a single item, and we tweaked the B star i's so that we got at least some version of that inequality with this extra 1/2 here. Yeah, that's what we've done. All right, so let's just start working through some corollaries in the m equals 1 case, okay? There's a couple differences. And so first price auctions are better behaved than second price auctions in a few respects, okay? So you might think that, in the second price auction, where, we had coefficients of 1 and 1, and we suffered a 1/2 in the price of Anarchy, now that we're getting a seemingly weaker lower bound of 1/2 and 1, you'd probably expect us to get a price of Anarchy that's worse than 1/2. Right? Because we had 1/2 before, and now we're proving worse inequality. Turns out we still get a 1/2. Okay? So let me show you why. So that's corollary 1. So for m equals 1, I'm going to prove something a little weird. So I'm just to help you understand the role so here's the new star. Okay, this is the what's the word? Deprecated star. Right. So I want to develop your intuition about what are the implications of what we just proved, this smoothness-like inequality in the first price case. So I'm going to show you that every pure Nash equilibrium has welfare at least 50% of optimal. This is sort of a stupid thing to prove per se, because it's very easy to prove that the pure price of Anarchy is 1. It's very easy to prove the pure equilibrium are fully efficient in the first price auction, okay? But again, the point, looking ahead to the extension theorems, the argument here will extend to stuff like Bayes-Nash equilibria, where we know the price of Anarchy isn't 1, okay? So that's why I'm going to do this. All right, so, and this will also show you why, because the first price auction is nicer, why the 1/2 doesn't degrade, despite the fact that it looks like it should. So here's a trick that's specific to the first price auction format. So remember, what we always care about, we want to say the welfare at the equilibrium is good. Okay? What we did in the second price world is we said, well, let's just lower bound this by the utilities. Okay? So this is like, if you think about it, this is a super sloppy step if we wanted lower bounds on the welfare, right? Because this is values minus prices, right? So we're taking the quantity we care about and we're adding a negative number to it just for free, and we're getting nothing in return, right? It just sort of, connected well with the rest of our argument, all right? So we're not going to do this anymore, okay? In the first price auctions, we can actually eliminate this sloppiness, and that's why we don't lose anything beyond the factor 2. So we're not going to do that. Instead, we're just going to say, well, look, let's keep track of player utilities and player payments separately. Okay, so this is just by definition. All right. Now this part, it's easy to see what this is, right? So we're summing over the players and we're looking at the price that players pay at the equilibrium. It's a single item auction, only one person wins, and it's the highest bidder. So this summed over all i's, this is just going to be a B max. Okay, that's easy enough. Now so now we do this. So now we use the fact that B is a pure Nash equilibrium. Switching to the B star deviations can only lower utility. So this is just this B max term plus I equal 1 to n, ui B star I B minus I. Okay, so that's just from the pure Nash equilibrium. Condition, and now we apply star. Okay, so that connects directly here. This is lower bounded by 1/2 V max minus B max, so the two B maxes cancel. Okay, and we're done. So what happened is, why did this work? Why couldn't we do this same kind of trick to do even better in the second price auction? Now remember, looking back, we had that matching lower bound of 1/2 for the second price case. So we actually know that in the worst case, we didn't lose anything by throwing it out. And actually, if you think back to that bad example, nobody pays anything. So that's why this inequality is tight in the bad unit demand example for simultaneous second price auctions. Now here, why is it that in the upper bound we can take advantage of this? It's because with the first price rule, it sounds glib, but the price you pay is exactly the bid that you made. Second price auctions, the price you pay can be much less than the bid that you make. And the way that plays out here is, on the left-hand side, we basically think of this as involving player utilities plus the prices they pay. So over here we have some extra term, the P's. And ultimately our error term on the right-hand side is the bids. Okay? So if the bids, the error term, is exactly the same as our sort of surplus we have to work with the prices, they can cancel out. In the second price case, it may be these prices are way smaller than the bids. Like maybe these are even 0 despite the fact that these are big. So there was no way to take advantage of canceling them out. It's really specific to the first price rule that the bids you have here and the error term and the payments, the slack you have on the left-hand side can be charged against each other. Okay? So that's good news. So actually, even though it seemed like we get something worse, we're still in the 50% range. And as I'll discuss at the end, we can even do better than that. Okay, so questions about that? So again, we're just sort of warming up, getting a feel for how to make use of this smoothness condition for the first price case. Okay, so corollary 2. This is a little bit of an aside, but it's pretty interesting. It'll give me an excuse to show you that sometimes you can get even stronger extension theorems that apply even for correlated distributions. So hopefully I've already instilled some degree of fear into you for correlated distributions with that wicked planted perfect matching lower bound. So that was when you had many items. Okay, so now I'm going to show you that if you only have one item, it's not so bad. Okay, you actually can handle the correlated case. So, let me state it over here. So corollary 2. Oh, and I should also say something. We made no overbidding assumption here, right? No overbidding assumption needed. Which you'd sort of hope would be true, right? I mean, it kind of seems, I mean, think about it, it seems sort of trivial, right? So if you're paying your bid, why are you going to, pay more than your value, right? That gives you negative utility, and you could always bid 0 and go home. Okay, but it's just nice to see it sort of like reflected in the proof, right? So that we don't have any last line where we invoke no overbidding. Okay, so when there's only one item, and it's a first price auction, Bayes-Nash equilibrium, the Bayes-Nash price of anarchy is at least 1/2, even for correlated priors. Okay. All right, so this is cool for a couple reasons, right? So the first reason, like I said, is that if we, is basically it's very rare you can get price of anarchy results for correlated distributions. We don't have a whole lot of examples. Sponsored search is the main kind of killer application where you can get correlated price of anarchy bounds. I think that's a project, but I'm not going to be discussing it in lecture. The second reason it's cool is remember, right, so, I mean, even for getting correlated, even if this was at least product and not IID, we'd already be in the regime where we know there's welfare loss, we know the price of anarchy is not 1, and we know it's basically impossible to figure out what the Bayes-Nash equilibria are, okay? So this is giving us good bounds, like well beyond where we can actually explicitly solve for equilibria. Okay. So, right, so morally, why is this going to happen? Right, how is it that we're going to get this? I mean, we'll see this reflected in the proof, but just, so that you're looking out for the right thing, there's something very special about these B star i's. Okay? These B star i's are simpler in a precise sense than the B stars we were talking about before. Okay? So what do you need to know to formulate this hypothetical deviation B star I?
Just VI.
And not V minus I, exactly. Okay? So that's exactly what makes it so that the extension theorem applies to correlated distributions, not just product distributions. So reason B star I function of VI only, not V minus I. Good. Okay. So you should keep an eye out for how that plays out in the proof. Okay, so let's start with what we care about. The welfare of our equilibrium. We're just averaging. So basically, all right, so I mean, I guess all of this is pretty easy to motivate. So all right, so our last Bayes-Nash equilibrium proof, why was it complicated? It was complicated because we had this doppelganger trick. Why did we do the doppelganger trick? It's because we needed an entire valuation profile to figure out what hypothetical deviation to do. So here, we obviously don't need the doppelganger trick. We can just directly do this bid. So this proof will be basically exactly like the very simple extension theorems we talked about last quarter, where literally you just sort of, keep averaging and you apply the smoothness condition, which in this case is the inequality star. You just apply this inside an expectation and everything just works out. Okay, so it's just really going to be a very simple proof. All right, so this is what we care about. Let's just sort of, copy. We want to get the 1/2, so we should copy the trick we did here of charging the prices and the bids against each other. So this is expectation of the utilities plus the expected payments. sorry, this should be sum over I, pi. Now, as usual, single item auction, the second thing is very easy to understand. In every valuation profile, exactly one person wins, and it's the highest bidder, and they just pay their bid. So this is just equal to the expected value of max I sigma I vi. Right? So one item, so the action is just a single bid. This is the highest bidder, that's the winner, and this is also what they pay. Okay, so that's what this becomes. Okay. So what about the utilities? Well, right, so now we use the, oh good, right. So now we want to use the equilibrium hypothesis, right? We want to use the fact that sigma's a Bayes-Nash equilibrium, so any legitimate deviation can only make you worse. And what we have going for us is that the B star deviation actually is legitimate. It's actually an option that bidder I could do at this moment because it knows VI, okay? So this is at most blah, blah, blah. Sum over I, ui. So again, the point here is that it makes sense to write what do I want to do? So let's see. So what notation should I use here? B star I. In all the other cases, past and future, I have to write the entire valuation profile V here, or some entire valuation profile here. I can just write VI. Sigma minus I, V minus I. Yeah. Good. Plus this payment term. And now, of course, we're right in the wheelhouse of our smoothness inequality. So inside the expectation is an inequality of this form. And so this allows us to disentangle the entangled term and lets us lower bound it by half of the relevant value profile, which here is just the full value profile V, plus the max bid in the given bid vector B minus I, which here corresponds to sigma of V, okay, the equilibrium bids at the valuation profile V, okay? So invoking star, we get blah, blah, blah. And let's see, this is 1/2 V max minus max I sigma I VI. Right, so this is the B max when the valuation profile is V and when everyone plays according to sigma. And then we're still inheriting this circled term here. Okay? And so now, just like we had cancellation for the pure price of anarchy proof, we have cancellation here between the payment terms. Again, this is the one that really corresponds to the bids. And then this is the one that really corresponds to the payments, but in the first price auction, they correspond to the same thing. So we literally just get 1/2 expectation over the valuation profile of V max. This, of course, is the optimal expected welfare. Okay? So we're done.
Why does 1/2 appear twice?
Oh, sorry. That was a mistake. Thanks. One aside I forgot to mention, which is back to the pure proof. This is a smoothness argument in the sense of last quarter. So this already, for the full information case, which again is not really the one we care about, but just to kind of close the loop, this corollary 1 extends to mixed Nash equilibria, correlated equilibria, and coarse correlated equilibria by the arguments from last quarter. And then corollary 2 is what handles the incomplete information case. And again, I want to emphasize this is a different argument. So really, for Bayes-Nash equilibria, there's a few different extension theorems, which take as input smoothness inequalities like star and basically produce as output a Bayes-Nash equilibrium bound. Most of them are almost identical. This one, this proof of corollary 2, this one is different. Okay, so this is a class by itself and worth kind of separating. There are much fewer known applications of this one, but when this applies, it's great. Okay, it's a stronger result. You get all priors even if they're correlated. It's just a simpler, more transparent proof as well. Okay, so this is the happy case when this corollary 2 proof applies. So that's one of the reasons why I sort of digressed and showed it to you. Okay, but we won't see any other applications of this stronger extension theorem in lecture. Okay, so because the next step is to pass on to multiple items, and as soon as you have many items, you have to know which items to target. And to know which items to target, you need to know, it seems, you need to know what you get in the optimal solution. And to know the optimal solution, you need to know other people's valuations. At least that's sort of the state of the art. Plus, we have these lower bounds for correlated price of anarchy with multiple items as well. Okay, good. So questions about that? That's everything I wanted to say about the case of m equals 1. And now I want to show you how we can actually, without too much effort, extend this to the general m case. So any questions about single item? Okay. Whoops, let's leave that. Okay. Okay, so general M. So as usual, what I have to explain to you is how do we construct these deviations B star. So you give me the valuation profile. So we're now in the case of multiple items. We're again going to be treating exactly the same valuation class. Go ahead and think about submodular, but the proof works more generally for these XOS valuations, maximum of additive functions. So how do I construct these deviations B star from the valuation profile? Given what you know, it's exactly what you'd expect. Okay, so what was the difference between first price and second price with one item? Instead of going all in meaning your full value, going all in meant half your value. What do we do with multiple items in second price, given a valuation profile? We look at the items a bidder is supposed to get in the optimal welfare, and we went all in. So now all in, it's the same thing, except all in means just cut the old one in half. Okay? So let me actually spell it out in detail. So let me remind you the key property of XOS valuations that makes this well defined. So given a valuation profile with an opt allocation S star up to S star n, what we proved last week is that we can choose, because each VI is the maximum of additive valuations, we can focus on the additive valuation which is tight at the bundle S star I that I is supposed to get in the optimal allocation. Okay? So it only underestimates the valuation everywhere, but we choose one that holds with equality for this bundle S star I. So let S star I satisfy, first of all, So again, this is an additive valuation, so it's just specified by these aij's. And if I evaluate this additive valuation on the items that I'm supposed to get in the optimal solution, I get exactly the right number. And 2, it only underestimates everywhere else. Okay? So those are the A stars. And then we set B star ij to be equal to 0. Right, so you're only targeting the items you're supposed to get in the optimal solution, and for those going all in now means your valuation for that item j with respect to this additive valuation A star, but cut in 2. Sorry. It should be up here. Okay? All right, so now we're going to move into what's called simultaneous composition. And basically what the next chunk of math, which is not too long, is going to show is that because prices are additive, okay, it's just these independent auctions. What you pay is just the sum of what you pay in each. Because they're XOS valuations, we can basically think of your valuation as being additive, roughly, at least with respect to some bundle that you're targeting. Then any inequality, any smoothness inequality like this, which you proved for a single item, just by adding, will give us the analogous smoothness inequality for the entire simultaneous composition. Okay? So with the second price auction, we actually sort of from scratch proved an inequality like this, the smoothness-like inequality. Now what we're doing is we're only proving the analog of that inequality for a single item. We've already done that. And then show it just kind of automatically extends to the M item case. Okay? So this is like yet another degree of laziness that we're adding, right? So we already have this one tool to be lazy, these extension theorems, which say if you satisfy these smoothness inequalities, whatever the mechanism is, then you can conclude Bayes-Nash price of anarchy bounds. Now I'm even saying, you know, if you don't even feel up for proving a smoothness bound for the whole mechanism, just prove it for like this tiny piece of the mechanism, and that's good enough to get smoothness for the whole mechanism. And then at that point, you know, the next part of the next heavy hammer is the extension theorem. Okay? So we've done a double reduction. Okay? So from Bayes-Nash price of anarchy to smoothness, we're about to do the second reduction from smoothness of a simultaneous mechanism to smoothness of just one of the constituent mechanisms, which is what we've already done, the single item case. Okay? All right, so that's all right. So I'm not going to state simultaneous composition as a formal theorem, but that's what we're about to do. Okay. All right. So is there some way we can take? Right. So all right. Good. So can we? How do we just show that this reduces to a bunch of single item computations? All right. So. Now a bidder I, it doesn't have an additive valuation. It really has this XOS valuation VI, all right? But let's just, you know, for a while think about as if its valuation really was A star I. It's not, okay, that's an underestimate, but let's suppose it were. So U star I, it's going to be I's utility if it had the valuation A star I. Okay? So notice that for every bid profile, the sum of the player utilities, really, you know, in any bid profile, but in particular in these bid profiles, is lower bounded by the sum of utilities if I switch to the U stars. If I pretend that the valuations are not really the VIs, but rather these AI stars. And that's immediate from property true. Okay? So the additive valuations, the A stars, only underestimate the original values. So whenever I'm talking about player utilities, I only underestimate player utilities by switching to the added evaluations. Okay? So that's sort of should be a trivial statement. Now, and again, so why am I doing this? So I'm going to prove a smoothness inequality for the whole mechanism, but I want it to just reduce immediately to each constituent item. Okay, so that's why if the valuations themselves were additive, then that would be immediate. But with XOS valuations, you can basically think of the valuations as being additive for these kinds of computations. Okay. All right, so what I'm going to do next is, so now, with these preliminaries, I'm going to prove a smoothness inequality, an analog of this, but for M simultaneous first price auctions. Okay, that's this derivation. So, for every bid profile, okay, I want an analog of this, but for many items. So the left-hand side, as usual, we have to look at the entangled term. And to make my life easier, I'm going to switch to the added evaluations that are tight at the optimal bundles, the S star I's. Now, on the right-hand side here, the valuations are additive, okay? So if your valuation literally is additive, and you're participating in these simultaneous single item auctions, your utility just totally decouples across these items, right? Your payment just adds over the mechanisms, and with an added evaluation, your values just add over the different auctions, single item auctions, okay? So let's actually express this then just simply as a sum over the items. Okay, so focus just on some item J. And then we can just talk about the contributions to players' utilities from the auction happening for item J. So I look at each of the players in turn. This just means, you know, what you'd think it would mean. It just means the utility, the contribution of item J to the player's utility. This is well defined with additive valuations, okay? And I only need to know the action on item J to evaluate this, so I just want to know what is bidder I bidding in this profile, and what is everyone else bidding in this profile. Okay? So now forget about this. Just focus on this, okay? So the claim is, I mean, we already have a smoothness-like inequality for what's inside the parentheses, right? So there's some arbitrary item J, I don't care which one it is. Because I've switched to the additive valuations, each bidder just has some valuation, an A star ij for this item J. There's some deviation that we're thinking about, B star ij, which we chose to be exactly the way that we choose it for the single item smoothness inequality, right? So up here, so maybe I should have made this more clear, right? So for the single item smoothness, I wrote it just existentially. There exists these valuations, but really the valuations are just, you know, B star I is by definition VI over 2, right? So on this item J, bidders have these added evaluations A star ij. They're using exactly the deviations required for this smoothness inequality as if this was the only item auction happening in the world. And so therefore we can invoke our smoothness inequality for the single item case on this entangled term just on item J, okay? So again, so at a high level, this is what we want to disentangle. We switch to added evaluations, that's fine for a lower bound. Disentangling this boils down to disentangling each item J separately, and we know how to disentangle single items, okay? It is important that the deviating bids for the overall auction, the B star i's, project to what they need to be in the single item case. So remember, our smoothness inequality for a single item case is predicated on the deviating bids being half of the value, but that is exactly what we're using here. The B star ij is half of the local value A star ij. Okay? So the upshot is, just applying the m equals 1 case, for each j separately, what do we get? So we get the right-hand side, okay? So the highest valuation in this context, right? So locally, the valuation profile, it's as if bidder I has valuation A star ij. So this is just going to be the max of A star ij. Okay, so that's the analog of V max for item j. The analog of B max is just, in the original bid profile, who bids the most on this item j. Okay, so this is just going to be a max over all the bidders of what they bid on this item j. Okay? So this is a crucial point. I mean, so algebraically it's pretty trivial, but as far as conceptually, you know, it's great that things are just working out so beautifully. All right? So at high level XOS valuations, again, if you're just trying to lower bound these utilities, you can switch to additive valuations, and then everything just projects onto the items separately. They totally decouple. Okay? As long as you choose the deviating bids, so that locally on a single item auction, you get the right deviating bids for the m equals 1 smoothness bound, you can just apply it immediately. Boom. Okay? And now we're basically home free. We just have to rearrange and see that we have what we want. So any questions about that? Okay, cool. All right, so what do we got? So let's try to understand why we're done. All right, so first let's start with these. So let's bring out the 1/2. So sum over the items of the biggest A star ij on the item. So let's write that. So let's group the items as follows. Let's go over the bidders one by one, and then let's group it by who wins what in the optimal allocation, S star I. Okay, so again, I've just taken these m terms, grouped them according to who wins what in the optimal solution. I'm going to take these m terms and group them according to who bids what, who wins what in the equilibrium. Okay? But either way, so what is this? What is that equal to? How do we choose A star? What's the point of A star? Right, so we had this bidder that didn't have an additive valuation. Actually, it just had a XOS valuation VI. But we said, well, it's a maximum additive valuation. So basically, we can pick our favorite set, make sure we represent that exactly with one of the additive valuations while only underestimating everything else. And so we picked the additive valuation A star I that exactly represents the valuation on the bundle S star I. Okay? So by our choice of A star, this actually, so we've already, yeah. So this, the point is this is exactly equal to VI of S star I. All right, we chose A star to make it so. Okay, good. And so therefore, this whole sum is the opt welfare. Okay? So what we just proved, right, so what do we prove? We proved that this entangled term, okay, so we showed, given evaluation profile V, we showed how to choose B stars so that for every bid profile B, this entangled term is lower bounded by half times the optimal welfare, minus the sum of the equilibrium bids on the items that people won. That is exactly the inequality we had for the single item case. Okay? Entangled term, half of the optimal welfare, minus the sum of the winning bids on the items sold. Back then there was only one item. Okay? So this is exactly the same inequality for general M. Okay? Because it's exactly the same inequality, we get exactly the same version of, for starters, corollary 1. Okay? Exactly the same proof. I'm not going to write down the same proof again. So let me just say, remark. So first of all, so this is simultaneous composition, as proposed by Serkanis and Tardosh in the last stock conference. Okay? And as again, I hope you can see from the proof, it's pretty transparent. I mean, there wasn't anything about first price auctions per se in this argument. I mean, what this says in general is it just says, suppose with a single item, you can prove a smoothness-like inequality like this. Okay? And this was important, suppose bidders have XOS valuations over all of the mechanisms. Okay? So look, again, imagine that you're running a whole bunch of mechanisms in parallel at the same time, simultaneously. And imagine the bidders have XOS valuations across them. Then, as long as each constituent mechanism satisfies an inequality like this, then so does the simultaneous composition. Okay? And this is the proof. XOS valuations just let you project individually on each of the single items. Okay? So again, I've proven it to you for a specific case to keep it from getting too abstract, but I mean, hopefully from the proof you can see it's some general theorem, and it is. It's called simultaneous composition. So again, and so the point here is to go smoothness of the single item to smoothness of the composition. Or if you like, it reduces understanding smoothness of the composed mechanism to that of a single mechanism, which is much easier, usually. So, analog of corollary 1, and to remind you, corollary 1 said that the full information concepts holds by the same proof. So in our proof of corollary 1, this is where we first use the trick of canceling out the prices paid on the left-hand side with the bids made on the right-hand side to get our factor 2. That proof never used the fact that there was only one item. The only thing that proof cared about is that we had this inequality. Now we have exactly the same inequality, but for many items, so exactly the same proof works and proves the factor 2. And again, that's a smoothness argument in the sense of last quarter, so it extends to all the full information concepts. Now, corollary 2 is a different story. For one item, corollary 2 said that even for correlated prior distributions, we get a Bayes-Nash price of anarchy of 1/2. All right? We know that's false once we go from one items to multiple items. Okay, not quite. Last lecture, I showed you that for simultaneous second price auctions, it's false. You have a bad POA for correlated priors. It takes very little work to modify the example I showed you last lecture to show that for first price simultaneous auctions, it's also a bad price of anarchy for correlated distributions. Okay? So the corollary 2, the arbitrary correlated distributions, we're not expecting to just carry over to the general M case. We also, looking at the proofs, know why. For M equals 1, we could choose the deviated B star knowing only VI. Here we can't. Right, so here when we define the deviating bids B star ij, as usual I need to know what are the optimal goods that I get in the optimal solution, and for that I need to know all of V. So instead, for the general M case and for Bayes-Nash equilibria, what we want is we want an analog of what we got for simultaneous second price auctions, which was for every product prior distribution, we wanted the price of anarchy to be good. And so that's what we have. So this was proved not using simultaneous composition, but just directly by Hasidim et al. In EC a couple years ago. So for all product priors, the Bayes-Nash price of anarchy in a simultaneous first price auction is at least 1/2. Okay? So this is basically exactly the same result we had for second price auctions. Actually, it's a little better because in second price auctions we needed this overbidding condition. And here, as you'd hope, in a first price auction, overbidding takes care of itself. You're never going to see overbidding in an equilibrium because that would be negative utility. So the proof is basically the same. Okay? So basically you just combine the proof of corollary 1, by which I mean you take advantage of this trick of canceling out the payments on the left-hand side with the bids on the right-hand side with the doppelganger trick. So just to remind you briefly what I mean by that. So for the Bayes-Nash equilibrium, again, the question is what's the deviating hypothesis that you use? What you'd love to do is just use the deviations B star we've already carefully constructed, but you don't know the optimal solution because you only know your value, you don't know others. So you sample these doppelgangers. You sample these W minus I's. You know the prior, so you can sample doppelganger types, doppelganger valuations for the other bidders. Then you can say, well, if this was people's valuations, what would be the optimal solution? And in that thought experiment, you're going to get some bundle of goods S star I, and then this is just how you bid. Okay, so again, that's your, and again, the only difference with the second price mechanism is instead of bidding your full A star IJ, you divide by 2 to hedge with the first price rule. And then again, you have to use the product distribution assumption in exactly the same place. You do the switch between the V's and the W's so that you can apply the smoothness inequality that we have. So again, this is the crucial inequality that gets fed as input to that proof. You apply this inside the expectation, and then you get what you want. Okay, and again, these just take care of itself. So these bids just cancel with the prices on the left-hand side. There's no need to control these with some overbidding condition. Okay. So based on all the stuff you've seen today, you're all fully capable of just putting those ingredients together to do that proof. There's literally no new conceptual ideas that you haven't already seen in the previous arguments. Okay. All right. So any questions about that? All right. So just a recap and one comment on an optimization. So I know I've already said this once, but just because this is one of the main points of today, let me just make sure it's crystal clear. So there's 2 important tools that we've learned, okay? And they work really well in conjunction. Extension theorems and composition theorems, okay? So extension theorems we were introduced to last quarter for full information concepts like correlated, coarse-correlated equilibria. Today we've discussed for the first time extension theorems for Bayes-Nash equilibria. And the point of an extension theorem, so you only want to be responsible for proving a bound for some really simple equilibrium concept, like pure Nash equilibria of full information games. But you want to claim credits for much more general results. Okay? Today we wanted credit for Bayes-Nash equilibria of an incomplete information game, where in particular there's a prior. Okay? There's some prior. And so what I've shown you, and this is principally the doppelganger trick, but we also had this other extension theorem that handles correlated distributions. If you're lucky enough to be able to devise deviations that depend only on your valuation and not on those of others. But the point is, you prove a smoothness-like inequality. So this is an example. So that just means one of these disentangling arguments. You prove a disentangling argument like this, or like this. Notice these inequalities do not reference any distribution. Right? There's no prior here. Right? It just says for every valuation profile, there exists B star, so that for every bid profile B, blah. Okay, there's no distribution in this statement. So you prove a distribution-free statement, and using one of these 2 extension theorems, you get the exact same bound. In this case, it was 1/2, all the way for Bayes-Nash equilibria. Okay, so that's the point of an extension theorem. You do the hard work, the manipulation, without a distribution, just purely on valuation and bid profiles. You get the conclusion, though, with respect to your favorite prior, either product or correlated, depending on the type. So you get your price of anarchy guarantee for Bayes-Nash equilibria. So that's tool 1, extension theorems. The second tool, composition, says, well, proving these smoothness inequalities, proving these disentanglement arguments, that's kind of hard work. Is there some way we can reduce these disentanglement arguments and make them simpler? And so what we saw for this particular case of simultaneous single item auctions is the answer is yes. Because there's a notion of composition which says if you're happy handling XOS valuations, and we'll talk a little bit next week about what's required to go beyond XOS valuations, but if you're happy with XOS valuations and its subclasses, then what? I lost my train of thought. Right, so then, rather than just directly proving smoothness for the entire collection of mechanisms, it suffices to just prove these disentangling arguments, these smoothness inequalities for one constituent mechanism. That lifts bi-additivity to the entire mechanism. Okay, so that's the second part of the reduction. So you wind up only having to ever actually prove, given this toolbox, you only have to prove that for something like so you recall how trivial the proof of this was? Do you remember? This was like embarrassing to actually write that out in class, right? So we proved that for a first price auction, whatever the valuation profile, if people just bid half their value, then this is true. And it seemed silly, okay? But that's in fact the only specific property we needed for this auction format to deduce then Bayes-Nash price of anarchy bounds for simultaneous first price auctions. The composition theorem pushes this to basically a full information model with multiple items. The extension theorem pushes smoothness for the composed mechanism out to Bayes-Nash equilibria. Okay? So that's the most important kind of high-level takeaway from these last couple of lectures. The one thing I just want to mention is a comparison between the two. Okay, so I've given you results for the second price rules and the first price rules. You might ask, does the theory advocate sort of one over the other? For example, from a welfare-bound perspective. So second price auctions, we know everything, right? So we have so what's weird is at the moment I've showed you equal bounds for both, 1/2 either way. Sort of for slightly different reasons, but we got the same bounds. From last week, we know that for second price auctions, that 1/2 is tight. Okay? Even for the full information case, even for pure equilibria, even for unit demand valuations, you can't do better than 1/2. Okay? I haven't shown you any lower bounds for product distribution, say, for first price auctions. All right? And in fact, you can do better than 1/2. All right? It's not that hard. I'll lay it out as an optional exercise. You can improve the 1/2. So this very simple argument. You can have a slightly more clever definition of B star I, which is actually randomized. Okay, so you deviate to a distribution over scaled down versions of your valuation that improves the 0.5 to 1 minus 1 over E, where E is 2.718 ... Okay, so that's roughly 63%. Okay, so a more clever argument improves this 0.5 to a 0.63. As I hope is clear, that improvement's just going to cascade through every single result I told you today about first price auctions. Whether it was correlated equilibria, Bayes-Nash equilibria, correlated priors for one item, whatever. All the 1/2s become 0.63s. That's the state of the art. But that is strictly better than what is attainable with the second price world. So, if you want to use worst case welfare loss as a criterion, then it actually says first price is provably better than the second price rule. Okay? So I think that's enough for today. I'll see you next week.